Welcome back. This is the second session of today. In the screen we have session number 2 and the URL of the lab series BGP. So you also have that in your email sent by Melanie and also in the chat window. So I will click there. If you didn't register, you will have to register. Since I am already registered, I will log in. So this library is about BGP. It's intro to BGP. There is another library that is advanced BGP and other protocols such as MPLS. But this includes the basic of BGP from an intro, internal BGP, external BGP authentication, the main attributes such as autonomous system path, local preference, MET, and more. So I see in the chat window the observation is if we're interested in peer/student education, are these instructions on setting up a similar network emulation environment? So this environment I will be happy to share with you, William. So you can have access if you are teaching a class. Certainly we did that in the past and we continue to do so because we are under an NSF project. Particularly, I teach information technology students, so I teach this material. And yeah, it's at least for my classes, the material makes a difference. So this is the lab library intro to BGP. So we will be going through lab number 8. So I will click in lab number 8. And I will get a pot of equipment for lab 8. I have this. By the way, if I click on learn, I have all the lab libraries. In your case, you will have 3 lab libraries, the one that we're using today, but there are more lab libraries. Back to intro to BGP. And while this is starting, I will have an introduction to what this session will be. First, I want to give credit to Ali El-Sabeh. He's a PhD student at the University of South Carolina, and he's the main author of these lab libraries. We already talked about the labs, what is included in this library. The format of the labs is the same as Eli was describing for the network tools and protocols lab libraries. Each lab includes an overview, followed by section 1, which is the background information. For example, in lab intro to BGP would be the fundamentals of BGP, and then sections 2 to N includes the step-by-step directions. And again, this is literally a step-by-step, so any student can follow the step and should complete successfully the lab. For the BGP lab series, we use a router called FR routing or FRR. Some of you might be familiar, but I will go through one slide presentation about FR routing. This is an open source routing protocol stack, and the website is given here at the bottom. So the configuration is similar to other vendors' routers. For me, I have more experience with Cisco routers, so it's pretty similar to configuring a Cisco device. But FR routing is open source. It runs on Linux machines. You have a command line shell, you have a configuration file. Now there are some unique features, in my opinion. Protocols are implemented as independent processes. So here in the figure below, we have the protocols. We have a daemon for BGP, daemon for Ospf, daemon for RIP protocol, and there are some others. At the bottom, we have a process that controls the routing table, the routing information base, and that is Zebra. And then at the top, we have the command line interface, is VTY shell. And this is the interface that is used by the network engineer, the administrator. So that is a high-level view of FR routing. In the lab here at the University of South Carolina, for experimental purposes, we successfully, Ali is the one who was working more with this tool, and Ali, do you want to say something about your experience with the FR routing running on white boxes, so programmable switches? So what is your experience briefly with FR routing?
Yeah, so FRR basically runs natively on Linux, but it's also supported with other platforms. My own experience was like working with FRR with Sonic Network Operating System, and we were able to run BGP between two switches and like have full connectivity using BGP. And also static daemon was also supported. So we played with two routing protocols, the static routing protocol and the BGP.
And so we make experiments with specifically edge core switches, which is a white box, and then you can program the chip, the ASIC, the switching chip, and it works pretty well. Now, this is a very short overview of BGP because we will be talking about this during the lab exercise. The main goal of BGP is inter-domain routing. So BGP selects one path as the best path, and it places the selected path in the routing table. So we will see during the lab that there is a Bgp table, and we might have more than one path in the Bgp table to a given network. And the best path is selected by the Bgp process, and it plays the best path to the routing table. So what are the criteria for the best path in BGP? And this is the best answer I could put in a slide. Basically, there are several criteria. In this slide, we have 9 items. So BGP will start for the first item. Prefer the path with largest weight, and this is an attribute that is configured locally. If the weights are the same, go to step number 2. Prefer the path with the largest local preference, which is another attribute of BGP. If the local preference for 2 paths to the same destination are the same, go to 3, 4, 5, and so on. Eventually, there's going to be a best path. Now, without route manipulation, if we just use the default, at least with the FRR, the most common reason for path selection is step 4. And step 4 indicates that BGP will prefer the shortest path, and shortest mean the lowest number of autonomous systems to get to the destination. Now there is a question: what if we want to use another path that doesn't have the fewest autonomous systems? Well, in that case, the administrator can manipulate the weight. Remember, weight is first attribute here, or the local preference. And all this information is in, I want to make reference to the book by Rick Graziani, is in this book. So with this, what we will be doing is we will be configuring BGP from scratch. We will make a BGP work, and that includes iBGP, internal BGP, external BGP, local preference, if the time permit, at least until local preference. Before starting the lab, I want to mention a local preference because we will be using this attribute. So consider the case where we have a network. Let's say here is our network, autonomous system 64520. And autonomous system 64520 might receive the route 172.16 from different autonomous systems. One of them is 65500. The other is 65000. By default, if we don't use weight or local preference, etc., it's gonna follow the path with the lowest autonomous system number. But what we will do in this lab is we will see how to prefer another path by using an attribute that is called local preference. So local preference indicates to routers in the autonomous system which path is preferred to exit the autonomous system. So notice that there is exchange of BGP information between the internal routers. So these routers A and B will exchange local preference. And based on that, traffic to 172.16 will be steered in one way rather than in the other. So the default value on some routers is 100, referring to the local preference. And the local preference takes precedence over the autonomous system path. So the topology that we will be using is shown here. First, we have two autonomous systems to try to keep it small, but still we will be able to use these attributes. So autonomous system 100 is pretending to be an ISP. Then we have autonomous system 200 is pretending to be a campus network. We have three routers. Router R1 is part of autonomous system 100. And attached to router R1 is the network 192.168.1.0. I will be referring to the network as the number on the third octet of the IP address. So network 1 is 192.168.1. Router 2 is in the autonomous system 200 and has a network 2 attached to it. Router 3 is also in autonomous system 200, and we have the network 3 attached to router 3. Between routers, we have point-to-point networks, and for example, between routers R1 and R2, we have the network 12, network 1, 2. Between the routers R1 and R3, we have the network 13. And between the routers R2 and R3, we have the network 23. Other observations, we are using Ospf as an interior gateway protocol within the campus network. We will configure iBGP internally, and we will configure external eBGP between R2 and R1 and R3 and R1. Finally, the goal, first we will see how it works with the default values. And second, what we will try to do is we will steer the traffic so that any traffic leaving the autonomous system 200 will prefer this primary link. So we'll prefer this route rather than the bottom one. And we will use that, we will achieve that with the local preference attribute. So I will switch right now to our platform. And here we have, this is the topology. it's just one machine. We will be using Mininet. So we have the content here. I can download, and I will be opening in a different window. I will click on the client. So I will put on one side the topology, on the other side I will have the lab manual. So Ali, if you're going to be doing with me in case that at some point we switch the presentation.
Mm-hmm.
Okay, so.
But if you're going to be start configuring, you mean continue after? Because
I will follow this, just in case that we need something. You are.
Oh, okay.
You are pretty knowledgeable on this.
Okay.
So again, the first part is the overview. If we need a password, the password is password. And then we have background information about BGP, background information about local preference. And more information. Lab section 2 start our configuration. So that's where we will start. Again, the topology, this is the topology we were discussing, all the IP addresses. And we will start from a step or section 2.2. Okay, so first we will open Mininet, mini edit. Again, the password here is password. And we will, following the directions here, open, and the file that we have to use, the topology that we're talking about is in lab 8. Open, there is a directory called BGP labs. Here we have lab 8. Let me try again. All right, it's here. It may not look exactly as we have the topology, but let me put on one side. It really is the same topology that we were discussing. Notice that router R1, R2, and R3. So R2 and R3 are in the autonomous system 200. R1 is autonomous system 100. So it's the same topology. So then we will start Linux terminal. So it's right here. And what we will do is we will go to the directory that contains some files of lab 8. So cd bgp _ labs / lab 8. BGP labs lab 8. All right. The goal of this step is we have already a script that will be assigning the IP addresses to all the devices. Otherwise, it's going to take quite a bit of time to just assign IP addresses. The script is a config loader. And the file that have all the config IP addresses is lab8 _ conf.zip. So at this point, all the interfaces should have the appropriate IP addresses. We will exit back to our mini edit. And at this point, we can start the emulation. So here, run, we have, maybe I should enlarge this. Um, okay, so like this. We start our emulation. The buttons are grayed out, so they are not available. The emulation is running. I will skip this step. These steps are just to check that MiniNet is running and the configure the interfaces are correctly attached to the switches, routers, etc. I will also skip the figure 15 is to check that the host H1 has the correct IP address, single IP address. And I will go right away to here, step 5, page 13, which is we will start playing with the routers. Router R1. Again, right click, I'm holding right click, and I then let right click to go. And I have here the command line for router R1. Again, this is a Linux device. And in order to start FR routing, we have to start the Zebra process. And then we have to use the command line VTY shell of FRR. And this is the interface that is provided by FRR. It's a command line. Now, we can check what is the current routing table. Notice that router R1, it should have already the IP addresses in the configured to the interfaces. So show IP route is the showing the IP, the routing table. So what we have is router R1 is attached to the network 1, which is right here, switches 1, network 1. Network 12 between routers 1 and 2, and network 13 between routers 1 and 3. We can do the same. We can start FR routing in router R2, Zebra, VTY shell. Oh, okay. I'm trying to, all right, there. So Zebra, VTY shell, and we can check the routing table. So router R2 has the network 2 attached to it, network 12 between routers R1 and 2, and network 23. We will start also FR routing in router R3. So we have the routing table for router R3. Okay, so Ospf is not running, BGP is not running. So the only thing that has been done is the configuration of IP addresses, and the directly connected routes are already in the routing table. So what we will do next is to run Ospf on routers R2 and R3. Again, if we go back to the topology, what we have is R2 and R3 are part of the campus network, and they are running Ospf internally. So R2 and R3 should run OSPF. Now in FR routing, if we need to use OSPF, then we have to start the OSPF daemon. We didn't do so before, so what we will do is we will just get out of FR routing, exit, start the daemon for OSPF, and go back to FR routing. Now we are in router R2, so the daemon is running. That doesn't mean that we have a OSPF process building the routing table. So we have to configure OSPF, and to move to configuration mode in FRR is config terminal, similar to Cisco device. And then we have to start the OSPF process. So here we have the router command. We are starting an OSPF, but we will use again router command for BGP, or if we use other protocols, we will use the same command. In this case, it's OSPF. Router R2, notice that router R2 will need to advertise using OSPF the network 23. So 23 should participate of the OSPF process, and also the network 2. And we will do that with the network command. 192.168.23.0/30. So what that means is network 23 should participate of the OSPF process, and this network is in area 0. So OSPF is a hierarchical protocol. It organizes routers in areas, and area 0 is the backbone. We will only use one area. The focus here is not OSPF. By the way, we are also building a lab library for OSPF, where we will be discussing in much more detail areas and other features of OSPF. Then we will do the same for the network 192.168.2.0, which is R2 wants to advertise to 0. So 20/24, same area. And at this point, we will, those are the only two. We will not deal with the network 1.2. The network 1.2 between routers 1 and 2 really is the point-to-point link connecting to the external autonomous system from the point of view of R2. So we will just wait for that. And we will do the same for router R3. Again, we have to exit because we have to start the OSPF daemon. And then we have to, again, go back VTY shell to the FR router. Configuration mode. We will start the OSPF process. And in this case, we are in router R3, so we have to advertise from R3 the network 23 and the network 3. So that's why we have here network 23 and 3. Okay, 23.0/30 area 0. Same with the network 3. This is /24 area 0. And that's all we will do with router R3 for now. we can check the routing table. I will continue just to save time, and we will start with the Bgp configuration. Okay, so back to our topology, we have router R1 running Bgp, and R1 has two neighbors, 2 and 3. And then R2 and R3 will be running also Bgp. That's what we will do next. Let's start with router R1. We're exiting again FR routing because we have to start the daemon. Certainly, we could just start all the daemons at once, but what we want to do is we try to emphasize, okay, let's start BGPD because we are using BGP protocol. If we don't use a protocol, we don't need to start the daemon. BGP daemon and then back to FR routing. We will move to config mode. And then we will start BGP on router R1. Again, the command router, same command that we use for Ospf, this time it's BGP. And BGP requires the autonomous system. So R1 is running on the autonomous system 100. So the parameter here is the autonomous system number. We are in router configuration mode right now, and we can issue the command that are available for BGP. BGP has, again, two neighbors. The first one is router R2, and the IP address, one of the IP address of router R2 is 192.168.12.2. So what we're telling BGP here is you have a neighbor 12.2, and the neighbor is in the autonomous system 200. Like that. Now at this point, router R1 knows that it has a BGP connection. In fact, probably already established a TCP connection to exchange the BGP packets. And also it knows that this is an external BGP because the router R1 is in the autonomous system 100 and this neighbor is in 200. So this is an external BGP. Router R3 is also a neighbor of R1, and that's what we will do next. Notice that we have the IP address neighbor 13.2. This is router R3. Finally, last step in router R1, we will tell R1 to advertise network 1. So R1 is here, network 1, 192.168.10/24, will be advertised through BGP. And again, this is the same command that we use in OSPF, same command that is used on RIP and other protocols. Okay, then we end router R1. Also, I will skip this step. I will show the BGP table later with much more details in next steps, next sections. And we will do the same for, we will configure also BGP on routers R2 and R3. So let's start with R2. First, we will exit FR routing because we have to start the daemon, BGP daemon. And then go back again with the VTY shell to FR routing. We will switch to config mode. And router R2 is part of Autonomous System 200. Remember, router R2 is here, is Autonomous System 200. R2 has two neighbors. One is R1. One of the IP addresses of R1 is 12.1. So neighbor 12.1 in Autonomous System 100. And also R2 has a neighbor, which is R3. And R3 has one of the IP addresses of R3 is 23.2. 23.2, this is R3 in Autonomous System 200. R2 knows that this is an internal BGP. Again, we are configuring R2 and we're telling R2 you have a neighbor in Autonomous System 200. Therefore, this is internal BGP. Finally, in R2, we will advertise the network 2 that is at the top. And we will use the command network again. And that will be all we will do for now in router R2. So we end there and we will switch to R3. In R3, we will exit. We have to, again, start the BGP daemon now that we decided to use BGP. And we have to go back to FR routing using the VTY shell. We will move to configuration mode. We will start the BGP process in this router. This router R3 is part of the Autonomous System 200. And router R3 has two neighbors. The first one is 13.1 in the Autonomous System 100. This is this neighbor is R1. The second neighbor is 23.1 in the Autonomous System 200. This is R2. Internal BGP, external BGP with R1, internal BGP with R2. This is 13.1. Autonomous System 200. This neighbor is R2. Finally, we will make R3 advertise the network 3. Notice that the network 3 is directly attached to R3. Okay. We will end and we will pause for a second and try to analyze what is the state of the network. So first we will check the Bgp table. So the BGP table. This is show IP BGP. I will highlight this command and the output. Okay. A few things here. Table version. Every time that there is a change in the table, this increment. Also, these are the entries in the BGP table. So the first row is the first entry. Then we have a second row and so on. We're looking at the BGP table for R3. There are some codes here. For example, notice that we have here destination network 192.168.10, which is right here. Again, we are in R3. This is a remote network 192.168.10. This is one path. This is one path, potential path to 10, and this is another path. And these codes here are the status code. So this is status code. There should be somewhere a status code here. The meaning of this, this is internal BGP. This is clearly not the best path. Then we have another code that is greater than symbol. This is the best path for the network 192.168.1. And the next hop, this is another attribute for the network to reach the network 192.168.10 is 13.1. So 13.1 is right here. Again, we're analyzing R1. Next hop is 13.1, and by default, this next hop is an attribute. I think we have some information about this. Indicates the next hop that is to be used to reach the destination. The default is that the next hop is the next autonomous system. For example, for this route, 13.1 is already the next autonomous system, which is autonomous system 100. Even the previous route, so another way to get to the network 1 would be go all the way around to R2 and then R1. Even here, the next hop is 12.1, which is also R1, because the next hop is the next hop in the next autonomous system. Those are a few observations about the BGP table. We will discuss more in a second. We will continue, so we will try to finish at least the local preference, and then we will talk about local preference weights. So what we will be doing next is to advertise some routes specifically. I will jump all the way to step 3, page 27. At this point, R3 doesn't have a path to the network 1, 2. We can check that in the routing table. IP route.
Excuse me, Dr. Jorge.
Yes.
I have a question here.
Sure.
Salgan is asking, how is the network 192.168.1.0/24 considered internal when it is going over the eBGP link?
Excellent question. Excellent question. Let me just go back to the BGP table. All right. This question referred the question, if I understand well, how is this an I internal? Again, this is router R3. We're looking router R3, and what it says here is we have a route to get to 192.168.1.0, which is right here. And then we have this status code internal. What that means is we can confirm that. Let me go one. This is the status code. And notice that here we have an I. Table entry was learned via an internal BGP session. So that is the meaning of this I here. So back to here. This I here, this entry was learned through internal BGP. So what happened is R2 told R3, I have a route to 192.168.1.0. How did R2 tell R3? Using internal BGP, because here we have an internal BGP connection. Now, the other observation, I didn't want to make this point, but this route, as far as I understand here, this is not valid yet, because we have to have an asterisk to be valid. And the reason why this is not valid is because, at least so far, the next hop is 12.1, which is router R1 right here. And router R3 doesn't know how to get to 12.1. So that's why we don't have the asterisk here. I hope that answered the question. Thank you for that observation. Let's go back in the next few minutes that we have. What we will do is in router R2, R3 doesn't know how to get to the network 12, which is the one that I'm showing. So what we will do is we will make R2 advertise. So I'm going to config mode. Again, router Ospf. And something that we wouldn't want to do is to just enable Ospf in this interface facing an external autonomous system and start sending updates, Ospf updates. And that's why we will make this interface passive. We don't want to send Ospf updates to router R1. So passive interface R2 ETH1. Again, R2 ETH1 is the interface facing R1 in router R2. And then we will tell Ospf advertise the network 12.0. The network 12.0 is here. Then we will end. And we will do the same in R3 because R3 is not advertising the network 1.3, this network here, to R2. So we will do the same in R3. Config mode, router Ospf. Again, we want to make passive interface the interface facing the other autonomous system. We don't want to share Ospf information with that autonomous system. And then 192.168.13.0/30 area 0. So R3 will advertise the network 1.3 through Ospf. We end. Okay, that's if we check the routing table, we will see few changes. I will not do that. I will try to get to local preference. We're already there, and then we will see what is happening. So probably at this point it would be good to check how is Ospf, or excuse me, BGP routing to a network in the external autonomous system. So router R3, we're in page 30. I will check the Bgp table. And again, notice that R3, in order to get to the network 1.0, the best route is to 13.1. So traffic is going through this link when the traffic is coming from router R3. So what we will do, our goal in this lab was to instead we want to steer the traffic so that any traffic coming from autonomous system 200 will be moving to the primary link here and going to network 1.0. So that's the purpose of what is coming next, which is the local preference. So let's configure the local preference. We will start with router R2. And again, the idea of local preference is R2 and R3 will communicate. Our local preference is exchanged between internal BGP, and in order for them to choose what is the path toward an external network. So router R2 config terminal. We will follow some commands here, a route map. All this is just to manipulate the local preference value. Following this command.
Excuse me, Dr. Jorge, we have another question here.
Yes.
It says, what would be a reason why you would adjust the local preference? Why would you prefer one path that has a longer AS path length over another path with a shorter AS path length?
Correct. Correct. Yes. I have an. Let me just go here. Is the same thing that we asked here in this introduction. Something that comes to my mind is you might have a path that has is shorter in terms of autonomous system hops, but has less bandwidth. For example, choosing the commodity internet for some reason might have a shortest autonomous system path, but then you might have a connection that is longer in terms of autonomous system that has more capacity. You might want to send to that path. That would be a reason, but I will open at this point our colleagues from, if we have any colleague from EPOC or ESnet, I'm sure that they have better answers than me, or Indiana University, or anybody who want to add on that.
I'm sorry, what was the question?
The question is, why would you want to choose a path that has more autonomous system traversing from your autonomous system to the destination autonomous system?
Yeah, so you would want to do that in the case that you had a higher bandwidth link. You maybe have a 1 gig someplace and a 10 gig someplace, and you want to push the traffic over that 10 gig link rather than the 1 gig link, regardless of the number of AS paths. Does that answer the question?
Yeah, thank you.
Sure.
But for the person who asked this question, that's a good observation. If you want to follow up with another.
I do have one follow up on that. Just to clarify, that only affects outbound traffic, correct?
That is correct. A local preference outbound. MET, which is it's also this lab. If we had more time, we will use MET for inbound, or to try to steer traffic for inbound. Not always is possible, because the other autonomous system also has the capability to use weights or local preference. But the answer is yes, you're right, as far as I understand.
Yeah, it is much harder to control inbound. The best way to do that is AS padding, and that's about the best you can do. But if someone sets a local pref, you don't have any control.
Thank you. Let's see if we can finish this we are on over time, but I will go. At least we will see the last result, how we are steering the traffic using the local preference. Here in router R2, we will set the local preference to 150. Local preference, the higher, the better. We will exit. So what we're doing is R2 is setting a local preference of 150. And this will be applied. We'll have to go back to BGP. And we have to apply this to the updates coming from our network 12, our neighbor 12.1, which is router R1. So route map, primary in. All right. And probably even with this, if we go to R3, the step here in R3 is setting let's try to complete rather than me talking. Config mode. We will set in router R3, we will have a lower local preference. So these two routers will exchange a local preference. They will agree that R2 has a larger local preference. Therefore, all the traffic coming from autonomous system or going to autonomous system 100 will follow the path through R2. Local preference for router R3 will be lower, 125. 200 up router, Bgp 200. And then we will set we will apply that local preference to updates coming from this neighbor. Okay. We can check the Bgp table. Hopefully, this is already reflecting our changes. So notice how the best path right now is through the next hub 12.1, which is right here. So basically, we changed the best path using the local preference outbound. Be able to see that trace route 6831. What is the destination? 192, 168, 110. Let's say traffic being generated in the network 3, going to the network 1. Going through 23.1, which is router R2. 12.1, which is router R1. 110, which is the destination. So that is one of the goals of this lab. This lab continues with the MET attribute. So I will stop here. So we are a little bit over time, 4 minutes. And when we come back, we will continue with the perf sonar exercise. So we will do, Cass, do you think 10 minutes, a break?
Yeah, I think that'll work fine. I'll come back at 3:15 Eastern. Thank you.
Thank you.